Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 2 of module 8. In this particular lecture we are going to use Microsoft Excel in order to solve an example of ODE boundary value problem using the shooting method. What we have been doing in this particular module is to look at methods to solve ODE boundary value problems, and the specific example that we are going to take, this is the example that we discussed in the previous module, is heat conduction in a rod. This rod is, let us say the length of the rod is 2 meters, one end of the rod is kept at 30 degrees Celsius, the other end is kept at 80 degrees Celsius, and this rod loses heat to the atmosphere is also at 30 degrees Celsius, and the overall equation that we obtain that we can obtain from this particular system is d square t by dx squared equal to beta multiplied by t minus 30, where the value of beta is going to be equal to 0.01. Okay. So this is the example that we are going to take in this particular module. In order to solve this by using a shooting method, we are going to convert this boundary value problem, of course subject to two boundary conditions, that is T0 equal to 30 and T2 equal to 80. This is what we are going. This is the problem that we have. We are going to convert it into an two first order ODEs, and in order to do that, we are going to write our y equal to t and z equal to t dash. So our first equation is going to be dy by dx is going to be nothing but z. So our first equation is dy by dx equal to z. Our second equation is d by dx of dt by dx, and dt by dx is nothing but z. So dz by dx is going to be equal to beta multiplied by t minus 30, t is nothing but y. So beta multiplied by y minus 30. Okay. And our boundary values are, the original boundary value is y0 is going to be equal to 30, and the other boundary value is y2 equal to 80. Okay. So this is our original problem. Okay. The way we are going to convert this into an initial value problem is we are going to guess z0 and modify these guesses such that finally we reach y2 equal to 80, and we are going to modify using bisection method. So this is going to be our strategy for ODE boundary value problem using the shooting method. Okay. So to recap, the boundary value problem that we are interested in solving is these two equations subject to these two boundary conditions. Instead of that, we are going to solve the same initial value problem with the condition y0 equal to 30, and we will keep varying the condition z0 such that finally we should be able to match the condition y2 equal to 80. So that is the problem that we are going to look at using Microsoft Excel. Okay, so what I have done over here, is I have written down, sorry. Okay. 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 Yeah. That's okay. Yeah, I'll just have water. Ready? Yes. Okay. So now we will solve this ODE boundary value problem using Microsoft Excel. Again, when I use the term Microsoft Excel, I do not necessarily mean you have to use Microsoft Excel in order to solve a problem. Any kind of a spreadsheet such as the OpenOffice or the Google spreadsheet is going to be good enough in order to solve any of the problems that we are doing in this particular module, or for that matter this entire course. Okay. So what I have written over here is the original the original boundary value problem. We have t double dash equal to beta multiplied by t minus 30. The value of beta was we have chosen as 0.01, so I will write that down over here. Okay, and t0 equal to 30 and t2 equal to 80. What we have done just now on the board is we have converted this into an initial value problem by substituting t equal to y and t dash equal to z. So our first equation is going to be dy by dx, that is y dash, is going to be equal to z. That is our first equation. Our second equation is dz by dx, which is nothing but t double dash. So dz by dx is going to be equal to 0.01 multiplied by t minus 30, t in this case is y, so y minus 30. Okay. So these are our two equations in two unknowns y and z. We require two initial conditions. The first initial condition is given by one of the boundary conditions, and that is y0 equal to 30. The second initial condition we will use z0 equal to guess. Okay, and these guesses will be made such that finally we are interested in satisfying the boundary value y2 equal to 80. Okay, so that is the value that we are interested in satisfying. So we will make these guesses such that we end up shooting accurately at y2 equal to 80. So this is our entire problem statement. Okay. So what we are going to do is we are going to use the midpoint method for solving the ODE problem. Solve ODE IVP using midpoint method. Okay, we have done this midpoint method in our previous module. I am going to recap this overall midpoint method. This time we are going to do this midpoint method for a two-dimensional problem. We have a problem in two variables. I will just zoom on to the full screen mode so that we can view the entire thing more easily. Okay, we will start off with so what we need to define is we need to define our h. We are going to define, let us say for this particular problem we will define h as say 0.01. okay. Again I will quickly go through the choice of h also in this particular example. So we will start off with x equal to 0, okay, and we will have y and our z over here. Y0 we are going to start off at 30 as I had said earlier. Z0 will start off as 0. Keep in mind z equal to 0 basically means that the gradient at the entry is going to be equal to 0. What that essentially should lead us to, that irrespective of whether we what numerical procedure we are going to follow, our temperatures throughout the entire reactor should remain steady at 30 degrees, because there is no heat transfer that is going to take place under these conditions. Okay, so let us see whether our method is able to get that or not. Okay, and now we require, for midpoint method, we will require K1 for variable 1 and we will require K1 for variable 2. Okay, K1 for variable 1 is going to be nothing but y equal to z value that comes over here. So, this is going to be our K1. K1 for variable 2 is going to be nothing but 0.01 multiplied by y minus 30. Okay. So, that is our, so K1 is obtained through this particular equation, our K1 for the second variable is obtained through this equation. So, K1 for the first variable is nothing but K1 equal to z computed at the location I, and K2 is nothing but 0.01 multiplied by yi minus 30. Okay. In order to compute K2 using the midpoint method, we need to obtain y. So, in order at the midpoint method, what we need is we require to compute f of x plus h by 2 and y plus h k1 by 2. Okay. So, this is the function value that we need to compute. So, basically we need the value of y plus h multiplied by k1 by 2. Okay. Likewise, we will need the value of z also. So, this is going to be yi, or I will just drop the subscripts and superscripts over here, h multiplied by k1 by 2, k1 by 2. Okay. And this is what we have, function, and just do format cells so that it looks better. Okay, and we will do format cells for here also. Okay. So, this is going to be y plus h k1 by 2, and likewise we will have z plus h k1 by 2. Okay. So, this is what we need for the computation of this function value. Okay. So, this is going to be equal to y plus h multiplied by k1 1 by 2. Okay. And we will put the dollar signs. This is what we have been doing all throughout. The h value does not change. So, instead of having B8, we are going to have $B $8. Okay. So, that is going to be y plus h k1 1 by 2, and we also need z plus h k1 2 by 2. So, z plus h multiplied by k1 2 by 2, and we can do again as before, we will put the dollar signs over here. Okay. And then we will basically need k2 1 and we will need k2 2. Okay. And k2 1 and k2 2 are just going to be computed in the same manner as before. So, I will just copy and paste, and we will just do F2 and we will see k2 1 is going to be from this particular equation. So, y dash equal to z. So, k2 is going to be z computed at the midpoint. The midpoint is given by x plus h by 2 comma z plus h k1 by 2. So, this is the value of k2 1. And likewise, the value of k2 2 is going to be equal to 0.01 multiplied by this guy minus 30. That is going to be the value of k2 1. Okay. Our next x is going to be x plus h, and again as always we will put dollars in front of this h. So, that is going to be our next x. Our y is going to be nothing but y plus h multiplied by k2, right. So, that is our midpoint method. In our midpoint method we have y I plus 1 equal to y I plus h multiplied by k2, and that is what we will have over here. I am sorry, I should be writing instead of h, I should be putting this particular guy, okay, and I will put dollars over there, so that whenever we are going to just drag and drop, we are not, that value is not going to change. And likewise z is I plus 1 is going to be z I plus h multiplied by plus h multiplied by k2, okay, and for h again I will put the dollar signs, okay, and this particular row I will just copy it to the next row, okay, and we will take this entire row and we will copy the entire row below 2 meters, okay. Okay, if instead of 0.01, if we had 0.02, if we had h equal to anything else, our results are not going to change, because the overall ambient is at 30 degrees, the initial condition is at 30 degrees. So, if there is no gradient initially into the system, the overall system is going to remain at 30. So, the results that we are going to get, or the results that we have obtained from the midpoint method do match our intuition. So, I will write this as midpoint boundary value problem with bisection, okay. So, now we are going to use the bisection method in order to solve this boundary value problem. So, what do I mean by that is what I am going to do over here is list out the various values that we are going to get. So, our y2 target is 80, okay, and what I am going to write over here is y2 calculated is going to be equal to the y2 value that we get is the y value at length of 2. So, that is going to be our y2 calculated, okay, and we are going to solve this entire thing using the bisection method, and okay. So, just resize this a little bit so that we can observe everything that happens, okay. Okay, so in this section, now this is the ODE IVP using the midpoint method, okay, and I will have this as the bisection method. Now, the bisection is what we are going to use in order to solve for shooting to our final solution. So, this is going to be our Z0 guess, and this is going to be our y2 minus 80. Okay, and yeah, okay, I have resized this a little bit more. Okay, so our initial Z0 guess was equal to 0. With that Z0 guess equal to 0, the y2 minus 80, this is what I will write over here, y2 minus 80 is going to be equal to y2 calculated minus 80. So, this is what we will get. Okay. So, y2 minus 80 is going to be minus 50. I will copy this and paste the value over here, paste special values, and the value is pasted over there. So, let us see what guess Z0 equal to 100 gives us. So, what I am going to do is the guess over here is going to be changed to 100, okay, and with the guess equal to 100, the value y2 calculated value turns out to be 151 degrees. So, I will copy this and I will paste this over here. So, okay. So, what we have is with Z0 guess equal to 0, we have our temperature as our temperature as 30 degrees, or the deviation from 80 degrees boundary was minus 50. The deviation from 80 degrees boundary using an initial guess of 100 was 151. So, now we are going to shoot at the midpoint between the two. So, that shoot is going to be equal to the previous guy plus the next guy by 2. So, that is the new shot is going to be 50. So, what we are going to do is we are going to take this value Z0 value, this is our Z0 value, and I will color all these guys also, so that it is easier for us to realize what is happening over here. Okay. So, with Z0 equal to 0, our deviation was minus 50, with Z0 equal to 100, our deviation was 150. So, we are going to change our Z0 to 50 and see what we get. With the change of Z0 to 50, the temperature is 130, whereas the deviation from our temperature is 50. So, I will copy that and paste it over here, and again I am only going to paste values. Right click and paste special values only, and so our next point has to be a midpoint between 0 and 50. So, that midpoint is going to be equal to 25. So, we are going to change that initial guess to 25. With that guess changed to 25, our temperature that we are shooting at becomes 80.334. We can copy this and paste it over here, paste special values. Okay. So, now again our value is going to lie between 0 and 25, that midpoint is. So, it is going to be equal to 25 divided by 2, okay, which is 12.5. So, we replace this by 12.5. Okay. So, when we change this to 12.5, what we are getting is that the temperature at the end of 2 meters ends up being 55. Okay. So, that is what happens over here. What I will also do is I will just plot the temperature, and okay, I will do insert and a scatter plot, as we used to do before. We will do a temperature versus the location plot. Over here. Okay. So, now let us go to full screen mode and see what is happening, so that we are able to see this in a more, we will get a clearer picture about this. Okay. So, when we took our initial guess as 100, what we want to do, we will also insert a line. Okay. So, this thin line is our target, that is the target we intend to reach, and we go to full screen mode. Okay. So, initially when we had our Z0 equal to 0, our temperature remained flat that is the thick line is the temperature profile, it remained flat, and we were shooting much below the intended value of 80. When we change this value to 100, we shot to the intended, instead of an intended value of 80, we hit at 230. So then we decreased this from 100 to 50, and with 50 we are hitting at the intended value, instead of 18 as the intended value, we were hitting that at 130 was the temperature at the other end. So next we tried 25 through the bisection rule, and we are now very close to 80. Again the error is 0.33. if this error is acceptable to us, we stop our iteration. If this is not acceptable to us, then we are going to change this again. So we said that was not acceptable to us, and we changed that to 12.5. with 12.5 again we are hitting this particular thing much below than where we expect. Okay, so with 12.5 what we get this value as is minus 24.8. Okay, so the next value is going to be between 12.5 and 25, because they lie on either side of the guess, and so the next value that we are going to try is 18.5 for Z0. Okay, and with 18.5 we are getting this as minus 12. Keep in mind that again we are shooting below the desired point. So now what we have done is the next value that we got is 18.75 as the next value from the bisection method. When we substitute 18.75 and then solve the ODE IVP using the midpoint method, this is the temperature curve that we are going to get. So the next guess of the temperature that we are reaching is less than 80, which is signified by the negative value again that we get of y2 minus 80, which basically means we are going to replace 12.5 as the guess, and so the two guesses that we are going to have is 18.75 and 25, and we are going to take an average of the two. So we will take 25 plus 18.75 divided by 2, that is going to be our next guess of Z0. We copy that and paste the value over there using paste special values, and now we have gotten again closer to the solution from when the guess was 18.75. the value over here is minus 5.95. again this value is negative, so we are going to replace 18.75 as the guess with 21.875 as the guess, and we are going to take the average between the two values, 21.875 plus 25 divided by 2. We are going to continue this. I forgot to tell you that we need to predefine what our stopping criterion is going to be, and in this particular example let us use a stopping criterion that y2 minus 80 should be less than 0.1. So we are fairly close with the initial guess as 25. Let us try to get even closer to that solution. This particular value has to fall below 0.1, the absolute value should fall below 0.1. So 23.4375, we copy that and paste it as our Z0 using paste special as we have been doing so far, and again as you see that this temperature has inched closer to the actual 80 degrees Celsius value. We copy this and paste it over here again using paste special, and because this is a negative value we are going to retain the solution 25 and replace the other solution with 23.43. So we will take the average of 23.43 and 25 which lie on either side of the solution, and this becomes our new average. We copy it and we paste it in the yellow block over here using paste special. Okay, and now the value that we reach is minus 1.24, that is the value that we have reached over here. Now again because this value is negative, we take an average between 24.2 and 25, that would be our next guess, and we will use this particular value and substitute it as Z0 using paste special as before, and now we have reached minus 0.45. Again this is negative value, so again we are going to take an average between 24.6 and 25 as our next guess. Hopefully which we should converge now. Again we have copied this and pasted it in the yellow block over here, which signifies Z0, paste special values, okay, and yes. So finally we have converged by special values. So finally we have converged to our solution. We will get the solution when our Z0 guess is approximately 24.8, and when the value of Z0 is 24.8, we have reached the temperature the temperature at the end of the rod as 80 degrees Celsius, and this is how the temperature changes. It changes linearly between 30 degrees Celsius and 80 degrees Celsius within the rod. So the problem that we had was one end of the rod was kept at 30, the other end of the rod was kept at 80, and there was heat loss taking place to the surroundings from this particular system, and this is the overall result that we are going to get from this particular reactor, okay. And this is how we have ended up approaching the overall solution. We took a guess value of Z0, based on the guess value of Z0 solved initial value problem and obtained the value that we will get at the end of the rod, and then we use that particular information in order to guess a new value of Z0, and we did that over and over again, and finally we reached the desired value that we were interested in, okay. So that is essentially how we have gone about solving this particular problem, okay. So now let us just recap what we have done. We will go back to our board and we will try to recap the overall procedure that we have followed in this particular example. So let us recap what we have really done in solving the ODE boundary value problem using the shooting method. The problem that we had was of the form d square t by dx square equal to, I am just going to put that as some function of t dt by dx and x, okay. I am just going to write this as a general function in this particular form, and the boundary conditions that were given to us were t0 equal to some value alpha and TL equal to some value beta. Instead of TL given to us, we could have been given T dash L equal to beta. So let us say if we had two different cases, we had or TL equal to beta or T dash of L equal to beta. This is also another possibility for the boundary condition. So now we had to solve this problem. This was the original problem. We converted this through change of variables, where variable y was defined equal to t, variable z was defined as equal to t dash. As a result of this, the equations that we got, the first equation was dy by dx was equal to z. The second equation was d by dx of dt by dx, which makes it dz by dx. So dz by dx was equal to function f of y, z and x, y comma z semicolon x, okay. And this were subject to the boundary conditions y0 equal to alpha, and the other boundary condition was either YL equal to beta or ZL equal to beta, one of the two conditions. So for example, if the other end is insulated, we will have ZL equal to beta, or if the other end the temperature is specified as it was in this particular problem, we would have YL equal to beta, okay. So this is the overall problem, and instead of solving it for y0 equal to alpha and yl equal to beta, instead of that we solve an initial value problem. Okay, and the initial value problem that we solved was dy by dx equal to z, dz by dx equal to f of f of y, z and x, subject to y0 equal to alpha and z0, not y, sorry, and z0 equal to some value phi, let us say this as phi. Okay. And when we solve this particular problem, this will give us y and z as a function of x. So, for example, the temperature changes like this and the overall dt by dz probably changes somewhat like this. So, this is how z goes and this is how y goes, and this is the value at yl. And let us say we had the problem of solving yl should be equal to beta, then we define our function capital F of phi as equal to yl minus beta. So, this is our capital F, where yl obtained by solving ODE initial value problem. Okay. So, what we did in our nonlinear equations part of the course, which was module 4, is this particular function f of phi was a function that was explicitly given to us. For example, the example that we took was 2 plus x minus ln x, sorry 2 plus x minus ln x. In that particular case, the function was explicitly given to us. We knew that this is the overall function, and based on that we could find out whether or certain values satisfy the f of x equal to 0 or not. In this particular case, we have not been given an explicit function in the variable phi, but we have implicitly defined this function in variable phi by solving this ODE initial value problem. Every time we change phi, our value y at the end of the rod changes. So, for one particular value of phi, for value of phi 1, we will get this as our yl. For certain value of phi 2, we will get this as our yl, so on and so forth. So, by solving this overall ODE initial value problem, as we change our initial value phi from phi to phi 1, phi 1 to phi 2, phi 2 to phi 3, so on and so forth, we are getting different values at the end of the rod. Using now these different values of the end of the rod, we want to ensure that they come as close as possible to the value beta. So, this is the problem that we are going to solve. So, what we did was we the first value we took was we took phi equal to 0 in the example that we solved using Microsoft Excel. When we use phi equal to 0, we got f of phi as minus 80. Okay. Next we use our phi equal to 100. That was the second guess that we took. Phi equal to 100 basically meant that the initial slope we gave was a very large slope. When we gave an initial slope as a very large slope, the temperature at the end of the rod ended up being something like 230. Because the temperature was 230 minus 80, we got that as a value 150, because these two values were on either side of the true solution, the true solution that we wanted is f of phi equal to 0, because they lied on the either side, we could use basically the bisection method in order to change the value from phi equal to 0 to from phi equal to 0 and phi equal to 100, we could change it to phi equal to 50. Instead of using bisection method at this stage, we could have used any other method of our choice. For example, if we had used the regular falsy method, we would have gotten phi 3 as nothing but 100 minus this guy minus this guy divided by this minus this value, the whole thing multiplied by phi at 100. That was how we got the regular falsy method. So the way we will get the regular falsy method is basically xi minus xi minus 1 divided by fi minus 1 whole thing multiplied by fi. So this is what we can do. So this is this guy, and the overall thing we can have that as 150 minus 80 divided by sorry, not 150 minus 80, that is going to be in the denominator. Have this as 100 minus 0 divided by 150 minus 80, so that is plus 80 multiplied by 150. So that is going to be our next guess of phi, and from phi 3 we can go to phi 4, from phi 4 we can go to phi 5, so on and so forth, and we can keep iterating that in order to get the solution. That is if we were to use the regular falsy method. And the final way to do this is we could have used a Newton-Raphson's method, with ODE IVP of our choice. Okay, and in the Newton-Raphson's method, what we have to solve is f of phi equal to our y computed at L minus beta. Okay, so this is the definition of f of phi, which should be equal to 0. This is obtained of course by solving ODE IVP. Okay, so we choose our phi 1, okay, that is our initial guess of phi, that is what we choose. The next guess phi 2 is going to be obtained as phi 1 minus f of phi divided by f dash of phi, where f dash we can obtain that as through using numerical derivatives. So what we can do is we can choose, say for example phi 1 we have choose as 0, we can solve ODE IVP, and this solving ODE IVP will give us YL. From YL we can get our f of phi, okay, and that will be just YL minus beta. Okay. Next we can solve ODE IVP for phi 1 plus delta phi. Let us say we choose our delta phi as 0.01. So we solve this overall ODE IVP for this particular value, solve IVP, which will give us the value of YL, which was obtained for phi equal to 0.01. Okay. From this we will get f of phi plus delta phi, okay, which is again the same as y obtained at the end of the rod minus beta. So now this particular value, let us call this value is nothing but f of phi plus delta phi, this value is nothing but f of phi. We can use these two guys, and our f dash of phi is going to be approximately equal to f of phi plus delta phi minus f of phi divided by delta phi. Okay. So, which we can write that as equal to y of L computed with Z0 equal to phi plus delta phi minus y of L computed using Z0 equal to phi, the whole thing divided by delta phi. Okay. So, we can use this particular expression for f dash, and then with this expression our phi 2, or in general our phi I plus 1 is going to be equal to phi I plus, sorry, not plus, minus f divided by f dash, and f dash is going to be obtained in this particular form. So, we can write this as minus y of L computed at Z0 equal to phi multiplied by delta phi. This whole thing should be divided by YL at phi plus delta phi minus YL at phi. Okay. We choose an initial guess for the initial value Z0, that is going to be phi 1, using phi 1 and a choice of delta phi. Delta phi we can take it as a relatively small value. In this particular case, for example, I have taken delta phi as 0.01. So, with choosing a small enough delta phi, we can calculate our y. So, that is in this particular case, that is the temperature at the end of the rod with the initial value being equal to 0.01. We have already computed the temperature at the end of the rod with an initial value equal to 0. Okay. The difference between the two divided by the delta phi will give us f dash. F divided by f dash is going to give us the amount by which we have to move our phi I. Okay. So, this is going to be what we get as the Newton-Raphson's method. So, what we have done essentially is converted ODE boundary value problem into an ODE initial value problem. We chose an initial guess or two initial guesses for which to solve the ODE initial value problem. If we have two initial guesses which lie on either sides of the solution, we can either use the bisection method as I showed you in Excel, or we can use a Regulai-Falsey method as I have demonstrated over here. So, we can use the Regulai-Falsey method or bisection method to get a new choice. An alternative way to do this instead of using a bisection or a Regulai-Falsey method is to use a Newton-Raphson's method, and if we were to use a Newton-Raphson's method, this is what our expression is going to be, where keep in mind this YL is the solution through a numerical scheme of solving an ODE initial value problem instead of having this as a given function f of x. Okay. So, this is the overall procedure for the boundary value for solving a boundary value problem using shooting method. Now, while the shooting method in principle is indeed applicable for this system, and we have shown in this particular example its applicability, one of the problems with the shooting method is that the ODE initial value problems that we obtain through this procedure are often going to be unstable. Now, we have seen what instability means when we talked about ODE initial value problems in the previous module. What we mean by instability is that under certain conditions we quickly go, our solution quickly reaches plus infinity or minus infinity for certain choice of phi values. Okay. So, if that is what happens from the overall system, we will not be able to solve the initial value problems. I will take up a quick example in the next lecture. So, in the next lecture of this module, we will start off with a quick example where this particular thing happens. We will go over that example, and then we will then go ahead and make a comparison between ODE boundary value problem solution for this particular example of temperature in a rod, and compare it with the ODE boundary value problem for the reactor that we are going to use in the next lecture. that we will motivate, that we will use to show certain problems with the boundary value problem solution using the shooting method, and finally we will go on to the solving this problem using a finite difference method. So that is going to be an agenda for our next lecture, and see you in the next lecture. Thank you.